decades, we've called Uranus and Neptune the ice giants. It's in the textbooks, it's in NASA mission documents, it's the entire identity of these two planets, and it might be wrong. In June 2026, a team at UCLA published a model suggesting that beneath their hydrogen skies, Uranus and Neptune may not be filled with exotic ice at all. They may be filled with magma, deep, planet-spanning oceans of molten rock with hydrogen gas dissolved into the melt like carbonation in a soda. If that's true, the two most neglected planets in our solar system have been miscategorized since before most of us were born. And the strange part is how little evidence we ever had for the ice in the first place. So tonight, the question is simple. What is actually inside Uranus and Neptune, and how do we convince ourselves we already knew? Here's what we can say for certain. One spacecraft has ever visited these worlds. Voyager 2 flew past Uranus in January 1986 and past Neptune in August 1989. It didn't orbit, it didn't drop a probe, it took pictures, measured gravity and magnetic fields on the way by, and kept going. Nearly everything we believe about their interiors comes from those two brief encounters, plus telescope observations from billions of miles away. For Neptune, that distance averages about 2.8 billion miles, or 4.5 billion kilometers. That's the number worth remembering because it explains almost everything about why this mystery has lasted so long. The ice giant story goes like this. Both planets are about 15 to 17 times the mass of Earth, but far less dense than a rocky world that size should be. Something in the middle had to make up the difference. Water fit beautifully. The logic came from planet formation. Uranus and Neptune might have formed beyond the solar system's frost lines, the distances where water, ammonia, and methane freeze solid. Out there, the thinking went. The building blocks of planets were mostly ice. So the standard model gave each planet 3 layers: a hydrogen and helium atmosphere, a vast mantle of hot compressed water, ammonia and methane, and a small core of rock and metal. But the deep ice in this model was never supposed to resemble the ice in your freezer. At millions of atmospheres of pressure and thousands of degrees, water becomes a strange electrically conductive fluid. Planetary scientists continued calling water, ammonia, and methane ices because these are volatile compounds that freeze in the cold outer solar system, and because they remain frozen inside the planets. The point is, nobody ever detected the watery mantle. It was inferred, the density matched, and the formation story made sense, and the labels stuck. Then, over the past year, 2 independent teams pulled on that thread, and the whole sweater started coming apart. The first study came from the University of Zurich on December 10th, 2025. Luca Morf and Revit Heled published a paper in Astronomy and Astrophysics that took a deliberately unbiased approach. Instead of assuming a composition and checking whether it fit, they generated huge numbers of random interior models and kept only the ones consistent with each planet's measured mass, radius, gravity, and rotation. The result was uncomfortable. Icy interiors worked, but so did interiors dominated by rock. The data we have just simply cannot tell the difference. Then came the second study, the one behind this thumbnail. On June 16th, 2026, Edward Young and colleagues at UCLA posted an extensively expanded preprint titled Ice Giants Revisited, Uranus and Neptune as Magma Ocean Worlds. The paper has been submitted to the Astrophysical Journal, but it has not yet completed peer review. Their idea came from an unexpected direction: exoplanets. Planets between Earth and Neptune in size are among the most common worlds revealed by exoplanet surveys. They are called sub-Neptunes, and many are thought to consist of rocky material surrounded by substantial hydrogen-rich envelopes. When researchers modeled those planets with a rocky interior under a hydrogen envelope, something surprising happened. At the crushing pressures where atmosphere meets rock, hydrogen dissolves into the molten silicate. The melting point drops, the boundary blurs. You don't get a rocky planet with an atmosphere sitting on top. You can get a deep, supercritical ocean of hydrogen-rich magma. Young's team asked a simple question. What if Uranus and Neptune are just the biggest sub-Neptunes we know? They built models with essentially 3 adjustable parameters per planet, and those models reproduce the observed radii, densities, gravitational fields, heat output, and even key features of the atmospheric chemistry. No ice mantle required. And there's a supporting clue from the planet's own neighbourhood, the comets and Kuiper Belt objects out there. The leftover construction material turn out to be surprisingly rock-rich rather than ice-dominated. The raw ingredients themselves argue against a purely icy recipe. A molten interior could also help with one of Voyager's oldest riddles. Both planets have bizarre magnetic fields, tilted far from their spin axes and offset from their centres, unlike anything at Earth, Jupiter, or Saturn. Fields generated in a relatively thin conducting layer rather than deep in a tidy, icy mantle might naturally come out that lopsided. So is it settled? No. And this is where honesty matters more than the thumbnail. The Magma Ocean paper is one model among several, and as of this recording, it hasn't finished peer review. The ice camp still has strong cards. In 2024, Burkhard Militzer at UC Berkeley published detailed simulations in which water, methane, and ammonia naturally separate into layers inside these planets, and his best-fitting models are almost rock-poor. Another recent model, developed by Roberto Tejada Arevalo, may explain why Neptune releases much more internal heat than Uranus. The difference could come down to mixing. A stable composition gradient may suppress convention inside Uranus, while stronger mixing inside Neptune allows more internal energy to escape. Water-rich, rock-rich, mixed, and magma ocean models can all explain parts of the evidence. Current observations cannot tell us which is closest to reality, and that matters far beyond our solar system cosmonauts. Sub-Neptunes are the most common type of exoplanet observed, but they are far beyond the reach of any foreseeable spacecraft. Uranus and Neptune are not technically sub-Neptunes, but they are our closest accessible laboratories for much of the same extreme planetary physics. If they contain magma oceans, they could reshape our understanding of planets across the galaxy. If they are water-rich instead, that points to a very different formation story. In 2022, the National Academies ranked a Uranus orbiter and probe as NASA's highest priority new flagship mission. NASA's 2026 spending plan assigns it $5 million, but the mission has not entered full development and has no official launch date. The once favoured 2031 and 2032 launch windows now appear unrealistic, so nearly everything we know up close still comes from Voyager 2, which passed Uranus in 1986 and Neptune in 1989. The Berlin Wall was still standing. So, the verdict. Are Uranus and Neptune ice giants? The honest answer is that the label may no longer deserve the confidence we gave it. The evidence currently supports a range of interiors, from water-rich to rock-rich to molten, and our existing measurements cannot pick a winner here. But what's changed in the past year is that the alternatives have become much harder to dismiss. The distinction matters because their interiors could reshape our understanding of how the outer solar system formed, help explain their strange magnetic fields, and reveal the physics inside one of the most common populations of planets found around other stars. And maybe that is the real lesson. For decades, a single name made one answer feel more certain than it really was. Distance limits what we can measure, but labels can make us forget how much remains unknown. So if you were running NASA's budget, would you spend several $1 billion on a mission that could take more than a decade to reach Uranus to finally discover what is inside and transform everything else we know about the planet? Tell me in the comments down below.